that I'm recording. No more mishaps like last day, although I think I can hear a little buzz. First and foremost, happy birthday to Francine. Can we... All right. So you got assignment 4. Assignment 4 is due next Thursday. Okay. It's really long, really big. So what I decided to do was, if you want to, you can hand in as a group. Okay. The thing is, so whatever group you work with, whatever, you all have to put your name on the same one, and then whatever grade you get the same grade, obviously, right? So this is more to encourage you to work together. I want you to work together, but I know that there's issues with, you know, what's plagiarism, what's working together. It's really kind of a fine line and hard to do. So, so if you are working with someone on this assignment, which I am totally expecting you to do, then maybe just put both names on there and you can share the credit. Okay. If you want to do it on your own, that's totally fine. It's just a bit more work. Yeah. Although if you're handing it in as a group, you should probably make sure that you're on board with the answers that someone else is submitting. I'm assuming you kind of do like a pooling thing. But anyways, you can figure that all out, but I'm giving you the option. Okay? And so you may submit, oops, what happened here? Assignment number 4. As groups. Okay. I think it's pretty self-explanatory that you have to share the marks, but the grade assigned will be the same for all members. Okay. So, all right. I gave you the formula, or another kind of weird formula sheet. I just photocopied the front of a textbook from another book. And so there's some stuff on there that you don't necessarily need. Okay, but the reason I wanted to get it to you was for the volume of the cylinder and the sphere, right? And so in case you don't have those, now you do. And then because I was gonna print just one page, I thought, hey, why not just copy another page as well? Why not? So now you have on the backs, you've got the graphs of some functions, right? So general shapes to keep in mind, right? So things that you might want to copy over to your own formula sheet, right? As we kind of go along and go through them. But for now, the only reason that I'm giving you this page of formulas is for the volume of a cylinder and a sphere for assignment 4, which is on the little, I had to take a picture of it, and I guess I angled the picture weird, so because the glare, anyways. So it looks a little wonky, but anyways. All right, so that's due on Thursday next week at the beginning of class. Any questions before we get going? No. All right. So what did we do? So last day, let's do a quick review. We talked about function arithmetic. Function arithmetic, where if we have a function, let's say let's say f of x and g of x. Okay. So given some function f of x and g of x, we can find f plus, jumping around here, plus g of x is a new function, right? So f plus g of x is a function, but what we do is we just say, well, that's the same as f of x plus g of x. Okay. And then things didn't really get surprising at all, right? Because if you're subtracting, and so just to summarize, f minus g of x is f of x minus g of x. F times g of x is f of x times g of x. And then f divided by g of x is f of x over g of x, as long as g of x is not equal to 0, right? We still can't divide by 0. So that was the function arithmetic that we went through and talked about last day. And now we're going to do something kind of similar in function composition in section 5.3. 5.3 is function composition. And I feel like the jury's still out on this course, right? Like, what should you be learning? What should we be doing? And everyone's got their own ideas. But Kate said, well, as long as you prepare them for calculus, that's good, right? So that you're at that kind of pre-calc level. And so I talked to Jason, who's teaching calc right now, and he said, the main thing that you need is function composition. So what we're about to do right now. So a little bit of those difference quotients that we talked about last day, right? But function composition is kind of a big one. This is not hard or complicated. So in the next few sections, the concepts are really small, but the applications are really long and big. So here we go. We're going to start by just defining a function composition. But really, instead of having, oh, I don't know what happened there. There's ghosts in here. Instead of saying, okay, well, f times g of x, what we're going to do is we're going to plug g of x into f of x, and that's going to be different, right? And so that's function composition. And so we're going to let f and g be functions where the real number x, is in the domain of f. Oops. X is in the domain of f, and the real number f of x is in the domain of g. And the real number f of x is in the domain of g. The composite of g with f denoted g and then a circle f, and my brain just wants to combine the O and the F to make gov or something. But anyways, so I really have to kind of try to space them out so it's not confusing for you guys. But this is read G composed with F. So the composite of G with F, denoted by G composed with F, is defined by the formula G composed with F of X is G of F of X. Okay. So we've done that before, right? When we said, okay, we want to find F of X plus H, for example, right? Then we replace all our X's with X plus H. So now we're replacing, so G composed with F means, okay, well, we're going to write out G, the function G, but wherever we see an X or whatever variable, we're going to replace it with F of X, another function. So it's a function inside a function. So I'll square this up. And let's do an example. If we let f of x be x squared minus 4x, g of t be 2 minus the square root of t plus 3, and h of s is 2s minus s plus 1. Right, so now we've got three functions, f, g, and h, that we can do stuff with. Okay. So part A, find g composed with f of 1. Okay. So I'm going to write it over here to give myself some room here. So G composed with F of 1, we can rewrite as G of F of 1. Now there's two main ways that you could do this, right? You can figure out what f of 1 is separately and then plug it into G, right? That's one way of doing it. Or what I'm just going to do is I'm just going to balloon this out and then simplify it back down. Okay. So G of f of 1 is the same as G of f of x was x squared minus 4x. But we've got x is 1, so 1 squared minus 4 times 1. Being really careful with all those brackets, right? So now, this is f of 1. That's going to become a number, right? And then we can find g of that number. Right? So this is the same as g of 1 minus 4 is negative 3. And g was 2 minus the square root of t, which is now going to be negative 3 plus 3. We've got 2 minus the square root of 0. Square root of 0 is 0. So we've got just 2. So G composed with F of 1 is 2. Sounds simple, but it's not. Right. Any questions about that one? Okay. How about B? Find and simplify. Find, simplify, and state the domain. That's that dang domain. Used to be so easy. And state the domain. Of H composed with G of T. So now it's not going to reduce to a number because we're just going to have that variable T still, right? But it's going to become a different function. So writing it out here, H composed with G of T is the same as H of G of T. And I actually prefer to write it that way on the right-hand side. I think it's just a little bit cleaner and a little bit more straightforward to look at. And so what we have is we have H, and then I'm just going to plug in G of T. G of T is 2 minus root T plus 3. 2 minus root T plus 3. So now, plugging 2 minus root T plus 3 into H, right, we get 2. So H was 2s over s plus 1. So wherever we see an s, we're going to replace it with 2 minus root T plus 3. So we get 2 times 2 minus root T plus 3 over s, which is now 2 minus root T plus 3 plus 1. Yeah. So you're going to want to keep your wits about you and make sure that you respect the brackets and just kind of work slowly because you don't want to miss anything, right? So dealing with the numerator first, I get 2 times 2 is 4 minus 2 times root T plus 3 over, and then in the denominator, those brackets aren't actually doing anything because it's just 2 minus root T plus 3 and then plus 1. So I can just simplify 2 plus 1 is 3. So we get 3 minus root T plus 3. And I don't see anywhere else we can go, so it's simplified. You cannot cancel the root T plus 3, right? Because in order to cancel it, well, it'd have to be a multiple of 3, but also a multiple of 4, which it's not. And so you cannot do that. Yeah.
Why can't you do it step before? Because that 2 is attached to the top
one. It's because, so we could if this plus 1 wasn't here. Yeah. So that's the glitch. Okay.
Why is H2?
H is 2s over s plus 1, but we're replacing s with 2 minus root T plus 3. So that's why we've got 2 times 2 minus root T plus 3, and then 2 minus root T plus 3, and then plus 1. Right? So we've just replaced the s's with G of T. Okay, so this is simplified. And I think as long as, you know, you've gone as far as you can and there's no more kind of brackets holding you back, then we can say it's simplified, right? Unless to me it's clearly not simplified, right? Then I'm not going to take marks off if you, well, I would if you didn't simplify this out, right? And so going from here to here, I don't know, it's kind of a natural step, right? But if you can't go any further, then, and it looks something like that, where there's no brackets anymore and there's nothing that you can cancel, then it's simplified, right? Because I know it's hard sometimes to know, well, how do I know if it's simplified, right? So if you've gotten rid of all your brackets and there's nothing that you can cancel, then it's simplified. Okay? So we're going to find the domain. Same problem that we're going to run into time and time again. We saw it first last day, right, where we were looking at the function arithmetic, right? We have to look at the individual functions, but also how they behave once they've been added or divided or whatever together, right? And so to find the domain, we're first going to find the individual domains. We were dealing with h of t is 2t over t plus 1, using t instead of s, but that's okay, right? We can just swap them out. They're just variables, so they can be anything, right? You can do h of smiley face, maybe h of sad face. 2 sad faces over sad face plus 1. Doesn't matter. Yeah. I had a prof in my undergrad, and he would always face the board and he talked really quietly, but it took me probably like half a term to figure out that he was calling them animals. All the variables he was calling animals. He was like, oh, and this animal here and this animal here, which is really funny. So he should have said it louder. But anyways, he just called them animals, and they are. So 2t over t plus 1. The only restriction here, remembering, so we go through our checklist, we cannot divide by 0. So anything that forces us to divide by 0, that's out of the domain. We cannot take the square root of a negative number, right? Anything that forces us to take the square root of a negative number, that's out of the domain, right? Those are our heavy hitters. And so here, because we're dividing, we already know that there's going to be something that's going to be pulled out of the domain. In this case, it's t equals -1, right? If we have t equal to -1, -1 plus 1 is 0. We're dividing by 0, that's a no-go, right? And so we've got the domain is just t cannot equal to -1. I'm cheating and I'm not using the interval notation, but I will later maybe, so saving it. So t not equal to -1. And remember, I'll specify if I want you to show it in interval notation, because we can't divide by 0. Right, just putting my little justification there. That's more a note for you. It's not for you to, you don't have to say that every time. And then we were working with g of t, which was 2 minus root t plus 3. T has to be greater than or equal to -3. Same deal, right? Up top, it gets confusing, I guess, because it's just a matter of what's easier, right? So in the first one, in h of t, I'm just pulling out one number. So then I'm just saying, hey, t just can't be -1. Here in g of t, I'm saying, okay, well, this is okay as long as t is greater than or equal to -3, right? And so I'll just put my justification here. Can't take the square root of a negative number. What we're going to do is now look at the composed function. You can look at the one that you made, but sometimes it's a little bit big and hard to deal with. And so it might be easier to just say, well, we wanted to look at h composed with g of t, which we can write as 2 times g of t over g of t plus 1. Right. So now, another part of our domain, or exclusion, I guess, is that g of t can't be -1. Right. So g of t cannot equal -1, right? Because then, again, we're dividing by 0, which is not allowed. So we solve g of t equals -1, right? And the result must be excluded from our domain. So we've got g of t, oops, I got weird. G of t is -1, which was 2 minus root t plus 3. So I'm forcing this to be -1 and then solving for t. So moving the 2 over to the left-hand side, I get -3 is negative root t plus 3. We can cancel those negatives, right? Technically dividing both sides by -1, right? Because here we're multiplying by -1. So to move it to this side, we're technically dividing by -1 on both sides, if you want it to be proper. But because -3 is negative root t plus 3, you can just drop the negatives. So then we have 3 is root t plus 3. We're solving for t, so we want to undo that square root, and so we square both sides, so we get 3 squared, oops, equals t plus 3. I'll do the squared square root. So we get 9 is t plus 3. Solving for t, I like to have whatever I'm solving for on the left-hand side, so I'm just going to move it over. But t is going to be 9 minus 3. So t must be 6. Okay. Therefore, t cannot equal 6 in the domain. You definitely could have just used our composed function, right? And said, well, at the end of the day here, after this composed function, once I've taken into account the domain for h and g, right? I also know that 3 minus root t plus 3 can't equal 0, right? And so here it would have been just as easy to say, hey, this can't be 0, so I'm going to set it equal to 0 and solve for t, right? We would have arrived at the same thing, but in general, right, for more complicated functions, right, it's going to be easier if you just write it out in general like this and just deal with the one function. What can that function not equal to? Any questions? No. And so, therefore, our domain for H composed with G of T is, all right, so we had to have, T had to be greater than or equal to -3, right? And also can't equal -1 and can't equal 6. Okay. So we have to start at -3. -3. I skipped my -1. -3 to -1. But I feel like I stole it. But -3 is smaller than -1. Anyways, here we go. Up to -1. Round bracket because it's excluded, right? -3, it's able to be -3, but then -1. And then to link these up, we do the U shape, right? The union. And then we start back up very close to -1, but not at -1, denoted by that round bracket. -1 up to 6, but not including 6. We start back up again at 6 to infinity, round bracket. Right. So here it is in interval notation. To go back and check why they didn't. Note to self. So that's from the original G and H. So we found the domain of H. H can't be, says that T can't be -1. And then G says that T has to be greater than or equal to -3. So that's why we start at -3. It's able to be -3. Then we have to stop at -1, pick it back up again, go to 6, stop. So there's little holes there.
So you have to figure it out for like the H of T and the G of T and then both of them combined.
Exactly. Yeah. So that's the hard part, right? Because otherwise, if we just said T can't be 6, that's not true, right? That's true for if it was just the straight function, but because we're taking from 2 other functions, we have to take those into account too. So it makes it tricky. Right. Any other questions about that one? Okay. So finding the domain is a little bit trickier now because we have to take into account all the functions that we used, right? All their domains, as well as the new domain. Okay. All right, how about another one? Find, simplify, and state the domain, again, of H composed with G composed with F. of x. Okay. Remember, you can treat g composed with f as a function, because it is, right? And so if you just block this out and say, okay, this is a function, so h composed with this function, and then you can expand it out and put in g composed with f. So you can have this kind of ballooning composed function. And as long as you do the order, it actually doesn't, or like h and then g and then f, it doesn't matter which way you do it. But you have to do them in the order that they appear. Okay. So this, we can rewrite h composed with g composed with f of x as h of g of f of x. Keeping track of your brackets. Bracket central. 1, 2, 3, few.
Did you say we were inside out or outside out?
Well, as long as you're wrapping this one around this one around this one. But if you're treating this one as a function, right, you can do that. Or you can treat this one as a function, but it has to wrap around f anyways, right? So it doesn't matter. But yeah, so we work this way, it collapses in, and it's always going to be like this.
Not at the top, at the bottom.
What's going on?
On the just talking math.
Yeah. The domain of the mountain range. All right, so you're just gonna keep your wits about you and just slowly plug in each function into the next one, right? So start with f of x, keep h and g around f of x, put f of x inside, and then build it out, and then build it out to fill in h. Okay. So I will move over to have more room. So I've got h of g of, and then f of x, I'm going to plug in. F of x was, steal it here. F of x was x squared minus 4x.
Since we already counted, don't count, we just use 2. Because the first thing we did was find g of that.
Yes, but this is g of f of x, right? And so we found g of f of 1. So we have to do it for x. But if you had found g of f of x, yeah, you could just plug those in. Okay, so this is good. I've plugged in f of x, that's gone. Now I can use x squared minus 4x in place of, I guess, t in g of t, keeping my h around there. So now g was 2 minus the square root. And instead of t, I write x squared minus 4x plus 3. There isn't really anything that we can do to simplify that, so I'm just going to keep going and plug that into h. And so h was 2s over s plus 1, so we've got 2 times 2 minus the square root of x squared minus 4x plus 3. Over 2 minus the square root of x squared minus 4x plus 3 plus 1. So we can simplify this a little bit, right? And so just multiplying through, I get 2 times 2 is 4 minus 2 times the square root. And actually ditch those brackets because they're not holding any negatives outside or anything like that. So we can just rewrite that as x squared minus 4x plus 3. Over 2. But this one I can't, the denominator I can simplify. 2 plus 1 is 3 again. So I'm just gonna jump right to that. 3 minus the square root of x squared minus 4x plus 3. That's as low as we can go, right? So we've gotten rid of all our brackets. We could maybe try to factor out, but I'm not gonna bother with the x squared minus 4x plus 3. It's not gonna do anything significant. So I'm just gonna leave it, right? As long as you've gotten rid of all your brackets and you can't cancel anything, like I said, then we've simplified. Oh, did you guys see on your formula sheet? There's also some special products and some factoring formulas that might be handy, right? Not for now, but just in general. It might be nice to have those somewhere. Okay. So let's find the domain. So domain, find the individual domains first. Individual domains first. The domain of F. Well, I guess I should write out the functions. We've gone long enough. F of x was x squared minus 4x. And so the domain is just all real values, right? There's no restrictions. There's no square roots. We're not dividing. And so it's going to be from negative infinity to infinity. G of t, or I'm going to write them all as g of x in terms of x, but it doesn't matter. 2 minus root x plus 3 has a domain. We decided already that x has to be greater than or equal to negative 3. And so writing it in interval notation just to mix things up, inclusive of negative 3 all the way up to infinity. H of x is 2x over x plus 1. So the domain is that x just can't be negative 1. And so we're from negative infinity up until 1. Sorry, negative 1. Because we've already looked at all these domains, but not in interval notation. And then starting back up again at negative 1 to positive infinity. That's the domain of H. Now find the domain of the composite function. We said, okay, we want H composed with G composed with F of X. which in just notation, right, is h of, well, I'll do it like this, g of f of x, because to me that's easier to handle. H, oh man, okay, here we go. H of g of f of x. Can we just all get along? Here we go. Yeah. Just thinking if there's a quicker way. Shortcuts never get me anywhere. But h of g of f of x. Because I was gonna do, maybe it's good practice, I don't know. Just go through and compose it again. Or another thing that we could do is we could just say, well, we're gonna end up at this point anyways, right? And so what we need to force, right, if we want to simplify things, is this is f of g, right? F of g cannot be -1, right? Or f composed of g, it's f of g, but sorry, g of f doesn't matter. Well, it matters, but you know what I meant. G of f plus 1, g of f can't be -1. You could just as easily go from here, right, and deal with this one. So it doesn't really matter. Yeah, you know what? In this case, we just might be better off just going from the one that we composed. Otherwise, we have to recompose it. Don't have to, but to show all our work. I'm gonna do that. Just like that, it's gone. We need to make sure that 3 minus the square root of x squared minus 4x plus 3 does not equal 0. Why did I do this? Why? G of f. This one. Oh, that's the problem. And x squared minus 4x plus 3 has to be greater than or equal to 0. That's the problem. So we start, okay. We start by solving the zeros, I guess. The zeros of x squared minus 4x plus 3. Oops, need a little 1. Greater than or equal to 0. Okay. X squared minus 4x plus 3, that's a quadratic. If you don't have it memorized yet, you will. A is 1, B. So then we've got negative b plus minus the square root of b squared minus 4ac. Now we're back on track over 2a. Which is negative 4 plus minus -4 squared minus 4 times a, which is 1, times c, which is 3, over 2 times 1. Yeah. Which is 4 plus minus the square root of 16 minus 12 over 2, which is 4 plus minus 4, square root of 4 over 2, which is 4 plus minus 2 over 2. 4 minus 2 is 2 over 2. And 4 plus 2 is 6 over 2, which is the same as 1 and 3. Oh. Nice. There, that's better. Okay. So now, right, we know that this function crosses the, and it's positive, right? Yeah. It crosses the x-axis at 1 and 3, right? And so at some point, the outputs will be negative and the other points they'll be positive. So we have to figure out between which values we can have, because we know that x squared minus 4x plus 3 is inside the square root, right? So it has to be positive, right, or 0. And so now we need to figure out, okay, well, what values make sure that it's positive? We need to find the values that make x squared minus 4x plus 3 greater than or equal to 0, since we can't take the square root of a negative number. So what I'm going to do is we'll just set up a number line. It's probably the easiest thing to do. So between 1 and 3, we know we've got this kind of transition, right? And so I'm just going to pick values in each of these regions. So I'll pick 0 and then 2 and then 4, right? And see how x squared minus 4x plus 3 behaves, right? So x squared minus 4x plus 3, when x is 0, is 3. Right? X squared minus 4x plus 3 equals when x is this number. So 3 is positive. So that's a positive region. So that's allowed. Right, so anything from negative infinity up to 1 is allowed, right? That's what that's saying. Now picking 2, just randomly, right? 2 squared minus 4 times 2 plus 3. 2 squared is 4 minus 4 times 2 is 8. So negative 4 plus 3 is negative 1. That's negative, right? And so between 1 and 3, that's out of the domain, which should kind of jive with what we were expecting, right? We had, and this is where it comes in handy to know what these shapes are going to look like, or approximately, right? Because we've got an x squared, so we know we've got this parabola shape, right? We've got a positive value, and so what it's saying is that it looks something like this, right? Crosses at 1 and 3. those output values are negative between 1 and 3, right, and positive everywhere else. So those are allowed. Okay. But we're just double checking that. So we don't rely on the graphs, but the graphs help. Right? And you could totally use the graph if you wanted to. But now plugging in 4 for our value beyond 3, we get 4 squared is 16 minus 4 times 4, which is 16, so 0, which is 3. So that's, we're back to positive 3. You don't seem convinced. How about I'll write what we gather from this. So now we know X must be or I'll do the exclusion, can't be between 1 and 3. So now, I say now a lot, on top of the original domain restrictions, we are also restricted by the domain of G composed with F, which has the domain negative infinity to 1. It can be 1 because that makes it 0. And then picking back up at 3, it can be 3 because that just makes it 0. That's allowed up to infinity. So we broke it down and found the domain of G composed with F. And then so we also know H of S has the domain S not equal to negative 1. Sorry, clean that up. So H of G composed with F means that G composed with F can't be negative 1. So G composed with F can't equal negative 1. G composed with F is that 2 minus the square root of x squared minus 4x plus 3. We're going to solve it to be negative 1 and then pull that value out of the domain, or those values. Okay. So if we want to move the 2 over to the right-hand side, right, we're left with negative square root of x squared minus 4x plus 3 is negative 1 minus 2. And this is going to be -3, negative square root of x squared minus 4x plus 3. Drop the negatives, right? You can divide the negative over on one of the sides, they'll disappear. And so we get the square root of x squared minus 4x plus 3 is 3. If we square both sides, we get x squared minus 4x plus 3 is 3 squared. So then we get x squared minus 4x plus 3 is 9. I'm going to move the 9 over to the left-hand side because then I'll have a nice quadratic equation and I can just use the quadratic formula. So I've got x squared minus 4x plus 3 minus 9 is 0. So x squared minus 4x minus 6 is 0. Again, you could try to factor it, but like I said, the safest way to do it is just to always use your quadratic formula, right? As soon as you have an x squared minus 4x minus 6 type of deal, right, where the highest power is x squared, you can use the quadratic formula, and it's the safest. So here we've got a is 1, b is -4, and c is -6. I'll just put a note here, solve using quadratic formula. So we've got -b plus minus the square root of b squared minus 4ac over 2a. And the quadratic formula is on the printout that I gave you. All right, so we've got -4 plus minus the square root of -4 squared minus 4 times 1 times -6 over 2 times 1. Which makes 4 plus minus the square root of 16 plus 24, 24, 30, 40, over 2. So I get 4 plus minus the square root of 40 over 2. Square root of 40 is just 2 root 10, but because that's going to cancel with the 2 in the denominator, I'm going to rewrite root 40 as 2 root 10. But if you just did it, you would end up at the same thing, 2 root 10 over 2. Now, because I've got 4 is divisible by 2 and 2 root 10 is divisible by 2, then I'm allowed to cancel. So this becomes 2 plus minus root 10. I don't know about you guys, but I have a hard time putting 2 minus root 10 on a number line, so I'm just going to convert it to decimals so I know where that's at. Since we need to exclude two plus minus root 10 from the domain, it is easier to think of them in terms of decimals. Right, so 2 minus root 10 is approximately 2 minus the square root of 10 is approximately negative 1.16227766. And 2 plus root 10 is approximately 5.16227766. That's going to be easier to put on our number line. We're still going to use 2 minus root 10 and 2 plus root 10 because those are the actual numbers, right? But now it gives us a better idea of where they go on our number line. All right. So now our domain, okay, here we go. We have to bake all these things in. So our original domains, you have them there, but maybe I'll just copy these guys to the bottom. Original domains. Domain, then we had to find the domain of G composed with F of X. Oops. Was what? Was this guy, right? Copy. Oops. And finally, we have to use and X cannot equal 2 plus minus root 10 from the final domain. So baking these all in, okay, so we have to start at -3, which also doesn't match what I copied down, so but I think the highest value, right? I don't know why they started at negative infinity, but it should be -3. Because you've got that domain of G of X.
Doesn't that just mean that you can be 3 or -3?
Mm-hmm. But it's saying G of X can't be any less than -3, so it has to start at -3. I'm feeling confident of that. And then we can go until we hit, I'll rewrite this one as, or -1.16 and 5.16. We can go until we hit -1.16 because the next stop is -1. So it can go up to 2 minus root 10 exclusive, so round bracket. Link it back up with 2 minus root 10, just like nothing happened. Because what we found was that 2 minus root 10 is one of the zeros. right? And so then we would be dividing by 0, because then g of f would be -1 if x is 2 plus or minus root 10.
Okay.
So then from 2 minus root 10, we can keep going until we hit, I want to say -1. -1, oops, negative bracket, -1 bracket, link it up at -1 all the way up to 1 now. Oh, 1 inclusive. Link that up with 3 to 5.16, which is 2 plus root 10, exclusive. Keep going with my unions here. Then 2 plus root 10 all the way up to infinity. So you're just baking in all your domains into one thing. And I am going to check this one out, because what happened to -1? Oh. Fun, right?
No.
No. What? I'm so surprised you say that.
Domains suck.
Domains do suck. You heard it here first. Okay. So from all our work, right, so that's the domain, that's done, great. Good work, guys. One thing should be obvious, that G composed with F is not the same as F composed with G, right? Because the order that we insert things matters, right? And so we see that G composed with F is not the same as F composed with G. But as long as we keep the order the same, as long as we keep the order the same, someone's watching like some show out there, I think. So as long as we keep the order the same, okay, we can compose in any order. Right. For example, suppose F, G, and H are functions. The associative law of composition says that H of G of F with brackets around G of F is the same as H composed with G and then of F. Provided that the composite functions are defined. Provided that the composite functions are defined. Wasn't I so nice and only made you do? Yeah, I only made you do 3 composite functions in question 6. So that's not bad. All right. I'm just going to mention the identity because it's not really going to come up. It's essentially, it acts like a 1. 1 multiplied by a number is just that number, right? And so that's the identity. And so the composition identity says that the function capital I of x equals x satisfies I composed with f is the same as f composed with I, which is f, for all functions f. It's not really groundbreaking or anything like that, but and we're not really going to use it, but I just had to mention it just in case it comes up later. Then I don't want to have to introduce it then. But it's more, so identity stuff we use more for matrices. So if you're doing linear programming and that kind of stuff, then you use matrices, but which you guys actually should learn about, but you don't. So maybe you'll get to learn about matrices, I don't know. Anyways, doesn't it sound fun and cool? The matrix. Matrix math is really fun. All right. Exhausted yet? Just lost. All right, that's fair. How about we talk about inverse functions instead then? I actually thought that I was going to run out of time, but here we are. Great. Section 5.6, inverse functions. Inverse functions are the last thing, so the last question on your assignment. So if we don't finish them today, then just hold off on doing that last question until Tuesday. But you should be able to do a good chunk of it. Because just like compositions, function composition, the idea of the inverse is not that crazy, but when we're doing them, it's a lot of work. Right, and so just like earlier, we started with just a quick definition. Here's what the composition is. Here's how we do it, and there's a lot of work involved. Same thing, here's an inverse. Here's how we do it. There's a lot of work involved. Okay, so the inverse of a function f is the function g that reverses the function f. Oops. So we'll start with our first kind of definition. Suppose f and g are functions are two functions such that the first item is that G composed with F of X is X. So it equals X for all X in the domain of X, or in the domain of F. For all X in the domain of F. And second point, F composed with G of X also equals X. For all X in the domain of G. Just as a fun note, did you know that the shorthand notation for all is an upside down A? For all. Fun. I figured since we used it twice, it was tempting. All right. So I'll put a box around this because we'll use this quite a bit. Okay. So if we have a function and a supposed inverse function, we can check that it's the inverse by doing the function composition, right? And so if we have a function and its supposed inverse, we can check algebraically by computing G of F of X equals X. Does it equal X? And F of G of X. Does it equal X? All right, so that's how we're going to use that little definition. Before we get there, though, we need to have some notation handy. And so we denote the inverse. We denote the inverse of F by F to the power of -1. And by the context, we know that since F is a function, right, we don't mean 1 over F. Okay? And by the context, we know F to the -1 does not mean 1 over F. Okay? Does not. Unless F is X, but that's the one case. Okay. Not all functions are invertible, though. Okay. And so we're going to talk about what it means to be invertible. And it's essentially if we can take an input and map it to a single output, and then a single output maps back to a single input, we call that one-to-one, and then it's invertible. Okay. And so a function F is invertible if it is 1-to-1. One-to-one says one input maps to one output, and one output maps to one input. So it has to be a function both ways, essentially, right? Must be a function both ways. Okay. A function f is said to be 1-to-1 if whenever f of A equals f of B, so whenever we have the same output, that's telling us that then A must be equal to B. They must map to the same output, or input, sorry. Oops. What this says is that we can check if a function is 1-to-1 by checking if f of A equals f of B reduces down to A equals B. Okay. And so we can check if a function is 1-to-1 analytically by solving f of A equals f of B and ensuring the result is A equals B. Or we can check graphically by seeing if the graph of f passes the not the vertical line test. The vertical line test is when the lines go up and down, right? That's to make sure that we have a function. To make sure it's 1-to-1, it has to pass the horizontal line test. And so now we can only have a horizontal line crossing the graph at only one point for it to be 1-to-1. Seeing if the graph of f passes the horizontal line test. Okay. Just as a quick example, we could have something like x squared, but when we do the horizontal line test, right? Oops. Does not pass the horizontal line test, therefore is not 1-to-1 and is not invertible. Yeah, so here, I was just doing these horizontal line tests there. So because it crosses the graph here and here, it doesn't pass the horizontal line test. So we check to make sure it's 1-to-1 to make sure that we can find the inverse, right? And so we don't have the inverse yet. So we need.
Oh no, because maybe it's the same function. This is the same function that f of a and f of b would be the same function.
Yeah, same function. And we'll do an example. I'll just do the sketch of, so if we have something like, not like that, like this, right? If we draw our horizontal lines, then we only cross the graph at one point, right? So this one passes the horizontal line test. So it is 1-to-1 and it is invertible. So we will be able to find the inverse. This one passes the horizontal line test, therefore is 1-to-1 and invertible.
One like that does the S. It comes up and down like that example. Back across.
Yeah.
But it would cross once it goes all the way up.
Yeah.
So would it count?
But as soon as it can cross multiple points, it's out. Yeah. So even if it is passing the horizontal line test for a section of it or a good section of it, as soon as you can cross the graph at 2 points or more, then it does not pass the test. Right. This is the same test that we did to determine if something was a function, right? But we use the vertical line test to make sure that it only crosses at 1 point, right? So now we're just doing the inverse of it, I guess. All right. Here are the steps for finding the inverse of a function. So once we have determined that a function f is 1-to-1, oops, 1-to-1. We can find its inverse by following these steps. One, right? Y equals f of x. 2, we're going to interchange y with x, right? So wherever you see an x, you're going to write y, and then for the y, you're going to replace it with an x. Interchange x and y. 3, solve x equals f of y for y to obtain y equals the inverse of f of x. Okay. So let's do an example then. Oops. Example. Show that g of t equals t minus 2 over 2t minus 1 is 1-to-1 analytically. So just by computationally, I guess, analytically by checking if f of A equals f of B means that A equals B. Confirm using Desmos and the horizontal line test. Desmos and the horizontal line test. Then we're going to go ahead and find the inverse. Confirm it is the inverse. Using function composition. Good. And then we're going to state the domain and range. State the domain and range of the original function. As well as the inverse. All right. We'll start at the top. But this one does look. Show that the given function is 1-to-1 and find its inverse. Check your answer algebraically using function composition and graphically using decimals. Blah, 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 blah. Basically the same. So, we'll start with the 1-to-1 mystery. I'll just rewrite g of t is t minus 2 over 2t minus 1. So what I'm going to do is I'm going to say g of A, does it equal g of B? Or I guess I'm going to force it equal to. But does that mean that A equals B? So g of A, you're just going to rewrite A minus 2 over 2A minus 1. And then g of B is B minus 2 over 2B minus 1. Now we're going to move the denominators over to the other sides, right? Multiply them over. And so we get A minus 2 times 2B minus 1 is B minus 2 times 2A minus 1. Just multiplying those guys over. All right, so now we're going to expand these and simplify, and hopefully we're going to arrive at A equals B at the end. Question? Okay.
Oh, you just moved the.
Yeah, so here, I've just said, okay, well, G of A, I'm going to replace all the T's with A. G of B, I'm going to replace all my T's with B's. So these are going to be the same, right? We're just going to rearrange them until we have it simplified. So now I'm going to expand this. Wish me luck. A times 2B is 2AB. A times -1 is minus A, minus 2 times 2B is minus 4B. -2 times -1 is plus 2. And then on the other side, here we go again. B times 2A, 2AB, minus B, minus 4A, plus 2. What I'm going to do is I'm going to shift everything over to the left-hand side and then start kind of, a lot of these things will cancel, right? So I've got 2AB. I'll write the initial left-hand side out first, minus A minus 4B. And you definitely could combine things immediately, but I'm going to show a couple more steps just so it's clear. Minus 2AB plus B plus 4A minus 2 equals 0. Two AB minus 2AB, those go away. 2 minus 2, that goes away. And what I'm left with is negative A plus 4A minus 4B plus B equals 0. And collect like terms. So -1 plus 4 is plus 3. 3A minus 3B equals 0. So now I can move that minus 3B over to the right-hand side again, so I get 3A equals 3B, and so A equals B, check. Therefore, G of T is 1 to 1. And therefore, it is invertible. Let's just check it in Desmos. So check in Desmos. What I'm going to do is I'm just going to sketch it out, kind of make a copy. It's not going to be nearly as good or as beautiful, but here we go. So whenever you're using Desmos, right, your variable, you can just use X because it's got the fixed X and Y axes, right? So we've got T minus 2 over 2T minus 1. So we've got X minus 2 and then divided by, oh, got to put brackets around, X minus 2 and brackets divided by, there we go, 2X minus 1. It's interesting that it knows that 2x is 2 times x. If we were using Maple, for example, which is just a big calculator, you'd have to specify that 2 times x, but anyways, it's nice. All right, so here, what happens is if we zoom in here, we actually have this asymptote, right, where it splits off. And so we've got this little tiny bit of space at, it turns out that it's 1/2 and 1/2. So we've got asymptotes on both sides, which we'll talk more about when we find the domain and range. But it looks like it's going to pass the horizontal line test. And because we did the calculations and found that it passed, then we can just assume that there's no overlap. All right, but this is what the graph will look like. Blah, 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 like that. Okay. So let's see if I can do something like that here. I think, was it, yeah, it's up a bit and over a bit. And then up a bit and over a bit. Oh. And so, because there's a slight incline here, it passes the horizontal line test. Oops, that was a nasty smiley face. There. And how about we'll do the rest of that on Tuesday, but you could probably just do it on your own. It's not skills that you don't know, so you can have a think on it, or you can wait until Tuesday, I guess. So long to wait. Unfortunately, hey, I heard unfortunately, so I'm happy. All right, let's see. See you later.